So this is 3.1.1 and also 3.1.2. We're doing progressive waves today. So we're going to explore two types of waves first. We're going to look at transverse waves plotted on two types of axes. And we're also going to look at longitudinal waves and then discuss their properties. So, starting with our transverse waves. If we draw them on a axis where displacement is on the x-axis, measured in meters, then this distance here is called the amplitude, which can be denoted by A. This distance here is the wavelength, which can be denoted by lambda. And our y-axis here shows us the particle oscillations. And these are in arbitrary units, which basically just means any units. Depends what we're looking at. So right now we don't have any context. In the case of looking at displacement on the x-axis, the direction of propagation of our wave is towards the right. So this is our direction of propagation. Now, we can also draw our transverse waves where the x-axis represents time. And again, here we've got particle oscillations. In arbitrary units. And in this case, this now represents the period of a wave, which is the time it takes to complete one oscillation. Other things you need to know is that the top of a wave is called the peak or the crest. And the bottom of a wave is called the trough. And then at any given time, you need to be able to recall the definition of a transverse wave. So a transverse wave is defined as waves in which oscillations are perpendicular to the direction of propagation. The direction of propagation is the direction in which energy is transferred in that wave. So in the case of the one we've drawn at the top, it's from left to right. And the oscillations are vertically up and down. Next, I want to draw longitudinal waves. And longitudinal waves are always quite difficult to draw. So I'm going to use these dotted lines as guides. That will help me to draw longitudinal waves. So usually you can think of these as coils on a spring. If the spring were to be oscillating, or you could send a wave through coils of springs that travel along the spring, causing compressions and rarefactions in that spring. So I'll draw these coils as straight lines between these two dotted lines I've drawn as a guide. So the lines might come out slightly bent, but that's okay. So what you can start to see is there are parts of the wave where the lines are far apart from each other. These are called rarefactions. And there are parts of this wave where these lines are closer together. These are called compressions. So I'm just going to continue to draw these lines. I think I'll stop there. So this again is our longitudinal wave. Now, I want to label from the center of my compression to the center of my next compression. This would be my wavelength if my horizontal axis is displacement. If x-axis is displacement, and it would be the time period if x-axis was time.
Would it start from the middle of the refraction of the start?
The center of one compression all the way to the center of the next compression. You could also do the center of a rarefaction to the center of another rarefaction, or any point along the graph which repeats again. But when we're choosing points, we choose the easiest points to reference. And compressions tend to be one of the easiest points to reference. So here, I'll just label this section as a rarefaction. And up here, we'll label that as a compression. And likewise with transverse waves, you need to be able to define the longitudinal wave. And as long as you are able to define the transverse wave, the longitudinal wave is very simple. It's the exact same thing. We just swap one word out. So longitudinal waves are waves in which the oscillations are parallel to the direction of propagation. I'm going to put a box around that. It's another definition you need to be able to recall at any point. Usually yes, but you should try and stick to propagation from now on. So the more you deviate from the way I tell you to, the more inconsistencies you bring in and the more misconceptions you also bring in. Waves in which the oscillations are parallel to the direction of propagation. Up here, that says rarefaction. It's when the coils, say for example, the coils or the particles have gone further apart from each other. Furthest, yes. So compressions are where they've come closer together. Rarefactions are where they've gone further apart. Yeah? Compared to how they were when they were in equilibrium in the non-wave situation. Next we'll talk about a new word which is called phase. Now, when you imagine waves, you should imagine sine functions or cosine functions, any trig function essentially. And what goes into a trig function? Sine of some angle, yeah? So if you think of sine of an angle, that angle tells you in which position that sine wave currently is in. Is it at its starting position, where it's about to increase? Is it in its maximum position, where it's about to decrease? And you have to know at which angles these happen in. So, before I introduce phase, I'm going to introduce some angles that you may not have yet learnt in maths, or you may have learnt in maths. So, up to now, you've worked in units called degrees. But from now on, I'm going to introduce some new units to you called radians. So, we're going to construct a table. So we've got 0 degrees corresponds to 0 radians. We've got 90 degrees corresponds to pi over 2 radians. 180 degrees corresponds to pi radians. 270 degrees corresponds to 3 pi over 2. And 360 degrees corresponds to 2 pi radians. So you should also know what the sine and cosine functions of these are. So sine theta we've got 0, 90, 180, 270, and 360. And then I'll also do the radian version. 0, pi over 2, pi, 3 pi over 2, and 2 pi. and then also cos theta. So 0, pi over 2, pi, 3 pi over 2, and 2 pi. Oh, I should have put that on the bottom. So let's fix that. If we select, bring that down here, and do the degrees version on top. So we've got 0, pi over 2, pi, 3 pi over 2. Sorry, I've done radians again. Let's fix that. 90, 180, 270, 360.
You do radians in your calculator.
You can do radians in your calculator, and I'll teach you how to switch your calculator back and forth later on. But for the video, I'm not going to show that in the video. So if you're someone watching at home, you should consult your mathematics teacher on how you can change your calculator to use degrees and radians mode and switching back and forth between the two. So let's then introduce this thing that I called phase. So phase talks about what currently that wave is doing, and then we can also talk about the phase difference. What's the difference between what each wave is doing? So typically the way I like to think about this is to think about soldiers marching synchronously. Their leg movements are a type of oscillation because it's a repetitive motion. And when soldiers are marching, you'll see that their legs are synchronized in their oscillations. So the soldiers are in phase. They are in step with each other. So in phase means in step. If you compare this with a random group of strangers, if they were told 3, 2, 1, begin walking forward, you would see that their leg motions are not in phase with one another. Their phase difference changes as well. Now, something can be out of phase but still have a constant phase relationship. For example, imagine a row of our soldiers marching, and then imagine a second row who are marching with their opposite legs. So when one row, the soldiers step forward with their right leg, the second row step forward with their left leg. They're not in phase with each other. They're out of phase by 180 degrees or by pi radians. Right? You can think of it as a wave. When the sine wave is at its peak for one soldier, the other soldier is at the trough. But as they keep marching forward, does the difference between their phase change? No. So they have a constant phase relationship in that state. So one cycle represents 2 pi radians. Or 360 degrees. Right, now we start a new page. This is where we're going to define lots of the smaller parts of a wave. And also I'll give you equations that relate these different things. So let's start with frequency. Frequency is the number of complete oscillations per second. It's related to the time period by the equation F equals to 1 over T. And frequency has units hertz or per second, but we prefer the units hertz. And the time period has units seconds. Next, we'll move on to the amplitude. So a quick sketch will help. Label that as A. And the amplitude is defined as the maximum displacement on the y-axis from 0 Next, we'll do the wavelength. And again, a sketch will help us out here. And the wavelength is defined as the distance from one wave to the same point on the next wave. We use the symbol lambda, and the units are in meters because it's a length. Then we've got the period, which is the time taken to complete one oscillation. We use T for that, and it's measured in seconds. And then I've got two wave equations to give you. S equals to CT. Now, this is where some of you coming from GCSE are going to have to change some of the things you're used to. S does not stand for speed. S is displacement. C is the speed of a wave. Oftentimes, it's the speed of light. Now, if you study in mechanics, or if you have studied mechanics previously, whether in maths or in physics, then this equation should remind you very closely of S equals to UT plus a half AT squared, with the half AT squared portion missing. because the wave is not accelerating. So with no acceleration, S equals to ut, or in this case, S equals to ct. So here S is displacement measured in meters. C is speed of the wave measured in meters per second, ms to the minus 1. And T is time measured in seconds. And the second equation I want to give you is C equals to F lambda. Again, this is an equation you're familiar with from GCSE. C is the speed of the wave, we mentioned already. And then I'll give you two values that you should roughly know. So C for sound is approximately 330 meters per second. Sometimes it'll be quoted as 340, sometimes 330. And then the speed of light, which you guys should already know, is 3 times 10 to the 8 meters per second. Now, we'll start a new page and introduce a new concept to you called polarization. Now, back in quantum physics, we talked about light as having wave-particle duality. We talked about light behaving as a particle. But from now, we're going to start talking about light as a wave behavior. Now, in order to understand polarization, you need to stop thinking about waves drawn on a 2D surface like paper, and instead imagine waves as existing in front of you. Now, if you've got some light shining upon a surface, the waves from that light are not all identical. They're not all oscillating within the same plane. So you can imagine some of them are oscillating. If they're moving, for example, from the front of the room to the back of the room, some of them are oscillating vertically upwards and downwards. Some of them will be oscillating horizontally. Some of them will be oscillating at some arbitrary angle, right? So they oscillate in all different directions. So we say that light oscillates in all planes. So a vertical plane would look like this. But it could have also a horizontal plane. So imagine it as oscillating in and out of the paper, right? In a 3D, we're thinking 3D now, not just 2D. So both of those waves of light, they have the same direction of propagation, left to right. And in both cases, the direction of oscillation is still perpendicular to the direction of propagation. And both of those waves are also perpendicular to each other. And we can have any arbitrary angle in between them. So if we were to look at all the waves of light, what it's actually doing, if we were to look at it from behind, for example, as it's moving forward, if we were following it from behind, it would look something like this. And it's moving into the paper, in this case into the whiteboard. So all the different waves here, they're all moving into the whiteboard. Yeah? So you're following the wave from behind. This is what you see. And they're oscillating in all these directions that I've drawn. And more. But I haven't drawn them all. Yeah? So, as a vector, any arbitrary directions can be resolved in 2 dimensions. A vertical and horizontal vector. So, as a vector, it can be resolved in 2 directions. So our 2 directions are vertical and horizontal. And light can also become polarized. And polarization means to make it only oscillate in one direction. So let's see how this would look. So here we have a simplified version of light, which is oscillating in its x and y plane. It's going to move from left to right. In front of it, we place a polarizing filter. So this is a polarizer. And it's a plane polarizer, so it polarizes in one plane. So this polarizer is a vertical polarizer, so I've drawn lines. You don't actually see these lines on them, but that represents that this polarizer is a vertically polarizing polarizer, so polarizing the vertical plane. So when light passes through this first polarizer, only those vertical components pass through. And the horizontal components, unfortunately, they don't make it past. However, there's an interesting point here. If we had components of the wave that were at some angle between those two, those ones will still get through, but they will change directions as they pass through. So a common misconception is that the polarizers block the light that's at 90 degrees to it. It's not actually blocking any light, it's trying to rotate the light into its own plane. But unfortunately at 90 degrees it can't do it. If it's at any other angle, it can let some of that light through as it's trying to rotate it across. So this light that manages to get through, well, that's now simple to draw because it's vertical. And then what we do is we can put another polarizer in front of that one, but this time we put a horizontally polarized polarizer. So now what we've done is we've crossed these two polarizers at 90 degrees to each other. And so no light manages to get through on the other side.
So what would you use it for? Like,
Camera lenses will use polarizing filters. Some sunglasses will use polarizing filters. So that's to reduce some light which can come off as glare. So we're going to talk about that in a second actually. So the next thing we're going to talk about.
so is that a horizontal polarizer?
Yeah, the second one is, yeah.
So why is the x-axis on the vertical wave diagram like that?
That's not the x-axis, rather, that's the direction of propagation. Because I didn't draw it in the first one, I can draw it in the first one as well. So the wave is going to move in that direction. Right? In the first one, it's oscillating in both x and y directions. But I didn't want to draw both of them oscillating at the same time because that's going to look very messy. So I didn't draw the actual wave as it oscillates in the first situation. I only showed it partially in the second one to show you that it's still oscillating, but the horizontal oscillation, so the x components, have disappeared after the first polarizer. Right, start a new page. So polarization is the only evidence that light, now be careful with my words here, not that light is a wave, but that light is a transverse wave, because it could have been a longitudinal wave. That light is a transverse wave, because there are other experiments that can demonstrate the wave behavior of light, right? But that's just wave behavior. That doesn't mean it's necessarily a transverse wave. So if we make a table, we'll put longitudinal and transverse. And then we'll put our different phenomena. So reflection, refraction, diffraction, interference, and polarization. So with longitudinal, all of these things happen except polarization, but all of these things happen with transverse. Now it's fairly obvious why you can't polarize longitudinal waves, in that they don't oscillate in different planes. They oscillate in one plane, which is the same direction that they travel in, the same direction as a propagation. Now let's look at some applications of polarization. About 12 years ago, roughly, 3D movies at the cinema were quite a big thing. Everyone wanted to watch 3D. So the way that the 3D used to work is that you had dual projectors projecting two images onto the screen at the same time. And each of these images were overlaid on top of each other. However, the light from each projector was polarized differently. And for the 3D effect to work, you had to wear these glasses. Each of the glasses, or the lenses for each eye, were polarized differently. So they would only pick up the image from each of those projectors, from one of those projectors. And so the way that 3D perspective works, the reason why we can see in 3D, is that our eyes are located at slightly different locations. So the images that we see from each eye are actually at different perspectives. So those two images that are projected by the projector give you two perspectives of that movie. And so it gives the 3D illusion. Right? We're still looking at a flat image on a screen, but it gives us that 3D illusion because we're given two different perspectives, like how our eyes would see. No, there's no evidence it damages your eyes. However, some people have felt a bit dizzy wearing them. Not to do with the glasses themselves. You could wear the glasses just fine, looking at other things. But because of the way that those two images are overlaid on top of each other, so there are certain artifacts that go on that could cause people to not feel very comfortable. Right? Now, other applications are, for example, in camera lenses. If you're trying to take a photo, for example, you get some artifacting called glare. For our viewers, they won't see it right now, but in this classroom right now, we can see some glare that's happening on that table on the far side where the sunlight's coming into the room. So the amount of sunlight falling onto that table right now has caused that table to become so washed out that that bright spot, we can't see any details on that, of that table on that bright spot. It just looks extremely white. But we know these tables are not extremely white. They have little dark spots on them as a design, right? You know, the false granite effect. But we can't see it on that table right now. So photographers don't want glare in their photos. Now what happens to light is, when light reflects off of certain surfaces, they become polarized. So that glare that's coming off of that table right now, that light is polarized. So if I use a polarizing filter, I can actually get rid of that glare, but keep the rest of the light from that table, and we would basically be able to see the details of that table again. It won't look washed out. So, if we have natural light here, which is unpolarized, as that natural light reflects off a surface, it becomes polarized. Reflected light is polarized. So it becomes plane polarized in the vertical direction. Then we can have polarized sunglasses or polarized glasses. Polarized glasses or camera lenses can reduce glare from reflected light. Yep.
When the light reflects off the surface, does it need to reflect at the same angle that it will?
Yeah, it does. The angle of reflection is the same as the angle of incidence. However, right now I'm just doing a quick sketch. It doesn't really matter how I've drawn it. So the purpose is, when it's reflected, it becomes polarized. That's the important information here. So if it's polarized and it causes glare, like on that table right now, and if you are watching this video, you're not going to see any glare by watching the video. So what you can do is Google some images of glare. And then we can reduce the glare by using a polarizing lens or a polarizing filter. So camera lenses or sunglasses will reduce that glare effect. And the image that you see or the image that you take with the camera won't be washed out. Another application is stress analysis. So if we had some perspex object that had some bends in it, we could cross some polarizers So crossed polarizers allows us to see colored bands. So you'll see like a rainbow effect. And the rainbow effect will be sort of like bent around certain places, showing the parts of the object that are under stress due to the bending. Which we call the stress lines. Among those, there are other applications, which I won't write down, but I'll mention them. So, for example, aerials that pick up signals, they tend to be polarized, so you pick up certain types of signals only. And LCD screens have a polarizing filter in them as well. Now, most common application would be the 3D glasses, the polarizing filter glasses, or the polarizing filter lenses for cameras. And that is the end of 3.1.1 and 3.1.2.